Good morning. Yesterday we derived the distributions of the arrival epochs Sn and the PMF of Nt. Today we will discuss alternate definitions of a Poisson process, alright. So, the definition we have seen of a Poisson process is that the inter-arrival times are independent and identically distributed exponential random variables. There are two other definitions which are equivalent. Okay, so, there are totally 3 equivalent definitions. So, that is what we will see today. Okay. The first definition is something we have seen already. This is basically that x I are I d exponential random variables of some parameter lambda. The second definition says following: a Poisson process is a counting process Nt that satisfies probability Nt equal to n as and independent increments. So, this is the second definition. It says that the Poisson process is a counting process that satisfies probability Nt equal to n is the Poisson PMF for all n is equal to 0, 1, 2 and for all t greater than 0. Okay. And it has to have SIP and IIP, stationary improvement property and independent increment property. This is the second definition. Now, so please note, the main thing to note is that just saying that Nt satisfies the Poisson PMF for every t and every n is not enough to specify a Poisson process, alright. If I just tell you that a counting process has Poisson PMF for every t and every n, Nt has a Poisson PMF, it is not enough. There are other processes which have that property. Okay. So, the Poisson process has the Poisson PMF and has SIP and IIP, then it is, then that is a unique specification, it turns out. So, we have already shown that first definition implies the second definition, right, because we defined the Poisson process as a this IID exponential inter-arrival times, then we derived the Poisson PMF from it, we also derived IIP and SIP from it. So, a process which the process as specified by first definition will satisfy the second definition, right. See, whenever you say that, see, when you define the same thing in multiple ways, you should show that they are equivalent, right, meaning that one implies the other. So, if you give two definitions, I should show that the first definition implies the second definition and the second definition implies the first definition, correct. So, first definition implies second definition, we have already shown. Second definition implies first definition, we have to show, right, that is pending. There is also a third definition, a Poisson process is a counting process Nt that satisfies the stationary increment property and independent increment property, stationary increment property, independent increment property and the following: probability that n tilde t comma t plus delta is equal to 0 is 1 minus lambda delta plus little o delta, sorry, little o delta probability n tilde t comma t plus delta is equal to 1 is lambda delta plus little o delta probability that n tilde t comma t plus delta is greater than or equal to 2 is equal to little o delta. So, the third definition here looks at increments in a small interval. Okay. So, second definition says you have Poisson PMF and SIP and IIP. Third definition says SIP IIP and a certain incremental specification, okay, over what does the process do in a small interval delta. Okay. So, if you look at this is time 0, okay, you look at some time t and time t plus delta. Okay. So, you look at the number of arrivals that occur in t comma t plus delta. Okay. It says this condition says that you essentially have 0 arrivals with probability 1 minus lambda delta, you have 1 arrival with probability lambda delta, okay, and this little o delta is a very small term. Okay. Are you familiar with the little o notation? This o is not big O, okay, this guy is a little o. Okay. So, little o delta basically means that, so a function is little o delta if little o delta by delta tends to 0 as delta goes to 0. Okay. So, little o delta is a term that contains delta squared or delta cube and so on. Okay. So, you might have seen this notation before, if you have not, essentially this is all that it means. Okay. So, you have 0 arrivals with probability 1 minus lambda delta plus little o delta and 1 arrival with probability lambda delta plus little o delta, and more than 2 or more arrivals is very unlikely, it is a very small probability little o delta. Okay. Now, so what it really says is that if you look at these sort of delta micro slots, right, if you divide time into these little delta micro slots, see the stationary increment property implies that it does not matter what t is, right. So, in any delta interval this t is irrelevant, in any delta interval there is this is satisfied, correct. An independent increment property means that if you consider these delta micro slots, the number of arrivals in each of them is they are independent random variables. Okay. And furthermore, what this is saying is that if you consider these delta micro slots, the Poisson process essentially looks like a Bernoulli process. What is a Bernoulli process? See, a Bernoulli process, it is a discrete time process. So, time goes not like not continuously, but t is equal to 0, t equal to 1, t equal to 2 and so on, and at each of these times you have a Bernoulli arrival, meaning that you have an arrival with probability p or no arrival with probability 1 minus p. You know what a Bernoulli random variable is, right. So, Bernoulli process means it is a discrete time process and each time slot you have a arrival with probability p, no arrival with probability 1 minus p, and they are independent across these discrete time slots. That is what a Bernoulli process is. Now, what we are saying, this definition is saying is that the Poisson process is very much like a Bernoulli process if you look at these micro slots, all right. So, in each of these little delta intervals there is an arrival with probability lambda delta and no arrival with probability 1 minus lambda delta, okay, and independent arrival independent increment property is satisfied. So, these Bernoullis are independent, all right, and of course, the t does not matter, right, stationary increment property.
Like it is actually continuous.
Which one? This definition? It is not a discrete time, it is a continuous time process. Now, all I am saying is that if you look at these small time slots of delta, in these little time slots, assume that delta is very small and it is going to 0. Okay. In these very little delta time slots, in each of these it behaves like an independent, it looks like a IID Bernoulli random variable whose arrival probability is lambda delta.
But can we say like that because it is continuous?
It is a continuous time process.
If we go on reducing the width also, it is still continuous.
It is still a continuous time process, but if delta is small enough, it looks like a Bernoulli process, that is all that we are saying. Okay. So, it is like a independent increment Bernoulli process as these time slots are becoming smaller and smaller. So, what we are perhaps this is an easier way to understand it. You consider a Bernoulli process, okay, where the time intervals are not 0 1 2, but 0 delta 2 delta and so on, okay, they are delta time slots, and in each of these time slots there is a arrival with probability lambda delta. Now, this arrival probability is not p, it is not a fixed p, but it is proportional to the width of the interval, and no arrival probability is 1 minus lambda delta. Okay. Now, in some sense, in fact your book does this in a more rigorous way. If you send delta to 0, then this Bernoulli process basically becomes a Poisson process. Okay. I do not want to get into the technicalities of it because I have not really defined convergence of stochastic processes and all that, right. It is a it gets a little more technical, but intuitively this is a very reasonable way to think about it. Okay. It is what is going on is a Bernoulli process in very small time slots, okay, where the arrival probability in every time slot is proportional to the width of the interval, right. It is not a fixed p, but it is lambda delta, okay, but there is ever so small a probability of having two arrivals. So, in that regard it is not quite a Bernoulli process. Bernoulli process means you have one arrival or no arrivals, right, but this Poisson process gives you a ever so small probability little o delta of having two or more arrivals. Okay, this is very small, but not 0. Okay. So, this little o delta it is a little innocuous thing, okay, but I will point out later that it is actually very important to have this. If you did not have this at all, if little o delta were precisely 0, then it is not a Poisson process. Okay. Some of these fundamental properties of the Poisson process will not play out if you have probability of 2 or more arrivals. If it were precisely 0, then some of these it is not a Poisson process, and some of the important properties of the Poisson process will not come out. Okay. So, little o delta is very small, but not really 0, okay, and this matters, and how it matters you will not see now, but I will point out later. Okay. It is not t goes to 0, I have written it is t greater than 0. So, this guy, so you are talking about this, right, maybe I will write this properly for all. So, I am just saying that there is a Poisson PMF for all t greater than 0. So, we have given 3 different definitions of the Poisson process, alright. Now, as I said, if you pretend to define the same thing in 3 different ways, it is better that you have to show that or they are all equivalent, right, which means that you have to show 1 implies 2, 2 implies 1, 1 implies 3, 3 implies 1, 2 implies 3, 3 implies 1, right. So, that is how many equivalences to show, 6 equivalences you have to show, right, or you can show that 1 implies 2 implies 3 implies 1, that is also okay, right, that is enough. So, we have to show that one, so there is some, so this is, so I am just putting a picture, okay, the definition 1, definition 2, definition 3, this implication we already know, right, because we derived the Poisson PMF and SIP and IIP from the exponential definition. Is 1 implies 3 easy? Let us perhaps we should do 1 implies 3, right. So, let us prove that 1 implies 3 for example. Okay. So, you have independent exponential interarrival times, you want to prove that n of t comma t plus delta satisfies that property, correct. So, see a process satisfying 1 meaning the IID exponential times satisfies IIP and SIP, correct, that I have already shown, right. So, the only thing I have to left to show is that, so IIP and P already shown, right, through that big theorem we proved, right. Now, I just have to show that probability of n tilde t t plus delta satisfies that incremental, right. So, you have to look at let us say probability of n tilde t comma equal to 0, right, is equal to, of course, this is equal to probability that n of delta equal to 0, right. Why? This is because of SIP, because I have already shown SIP, correct. So, in 0 to delta there should be no arrivals. What is the probability that there is no arrival in 0 to delta? This is same as the probability that x 1 bigger than delta. I proved this, no, n of t equal to 0 is the same as the event x 1 bigger than t, correct. Now, this is equal to what? E power minus lambda delta, right. Definition 1 says that x 1 is exponentially distributed, right. So, this is nothing but 1 minus lambda delta plus, so delta square delta cube terms and all will come, right. So, 1 minus lambda delta plus, so if you write out this in Taylor expansion you will get 1 minus lambda delta plus lambda del square by 2 factorial da da da, right. You will get delta square terms, delta cube terms and all that. 1 minus e power minus lambda delta you expand in Taylor, right, and this is just 1 minus lambda delta plus little o delta, correct. Next you can show that probability that equal to 1 is probability that n of delta. So, n of delta equal to 1, in 0 to delta you should have one arrival, which means that x 1 should be less than or equal to delta, right, and other you can, there is another way you can approach this, okay. We have already shown that there is an easier way to approach this in the sense that we have already shown 1 implies 2, correct. So, the probability that n of delta equal to 1 is, I know the Poisson PMF, right. I am cheating a little bit because I am not going directly from 1 to 3, you can do it, but I am saying you can, you already proven 2, but so you can use 2, right. This is logically correct, right. 1 implies 2 I have done. So, something I know from 2 I can use, right. So, I am cheating a little bit. So, this is from definition 2, but I have already proven 1 implies 2, right. So, this you can write it as, so e power 1 factorial will be down there, e power minus lambda delta whole power 1, right, which is lambda delta times 1 minus lambda delta plus little o delta. How do they get that? E power minus lambda delta I have expanded in Taylor. Yeah, I could have done the same thing. Yeah, see the, I have already proven that 1 implies 2, right. Now, I want to prove 1 implies 3. So, I am going through essentially what I am, what you are saying is that what I am doing by cheating is going from 2 to 3, right. So, this is, this is easy, right, 2 to 3 is easy. So, this is both, so you are right, 2 to 3 is also here, right. So, you are right, what you are saying is right. So, I am going, so I already went from 1 to 2. So, if I want to go from 1 to 3 I can go through 2, correct. So, these through, you are right, I do not disagree at all. I think what she is saying is that probability n of delta equal to 0, since I have already proven 2 I can use the Poisson PMF, I agree with it, right. So, now this is nothing but lambda delta minus lambda square delta square plus little o delta. Now, this guy is another little o delta term, right, because there is a delta square there, right. Okay. So, from this it is obvious that probability that n tilde t plus delta equal to 2, sorry, greater than or equal to 2 will be 1 minus probability that n tilde t plus delta equal to 0 minus right, because you it has to sum to 1, no, n tilde t plus delta will be 0 or 1 or 2 or bigger, all of this has to add to 1. Now, this guy is these guys I already know, right. So, this guy is already 1 minus lambda delta plus little o delta, this guy is lambda delta plus little o delta. So, if I add these two I get little o delta, correct. So, this will be just little o delta, correct, correct, yeah. So, I have shown that, so I have shown 1 implies 2 and 2 implies 3 and therefore, I have shown 1 implies 3. So, these are done, correct. Now, maybe so if I do this, right, I am done, right, if I do that I am done. So, if I take this Bernoulli view of this incremental delta incremental view of the Poisson process and prove that I get exponential inter-arrival times, then I am done, right, independent exponential arrival times, right. I will just sketch it, I mean I will let you do all the details. So, I will just point out how it goes, 3 implies 1. So, you are looking at, let us say that is my x 1, okay. See definition 3 looks at this sort of a delta view of the world, right. I want to essentially prove that x 1 is exponentially distributed with a parameter lambda and that the subsequent inter-arrival times are also exponential and independent of x 1, right. If these two I prove I am done. First let us prove that x 1 is exponentially distributed, okay. So, I want this, what is this? This is what I want to find out what it is, right. So, this means that in this t, so if you look at some t out here, okay, so you want the x 1 to be bigger than t, right, which means for the first t units of time there should be no arrival at all, which means that if you look at these micro slots there should be no arrivals, correct. So, there should be no arrival in this delta slot and no arrival here and no arrival here and no arrival and so on, right. So, the probability of not having an arrival in any of these micro slots is 1 minus lambda delta plus little o delta, correct. And how many are there? Approximately t by delta, correct. And whether you have an arrival in one micro slot or do not, they are independent. Why? Yeah, it is that is a part of definition 3, right, the increments are independent, correct. So, the probability of having arrival here and not having arrival here and not having an arrival here, these guys are all, you can multiply the probabilities because they are independent, correct. So, you will have roughly something like T by delta, okay. If you want to take something like that, okay, all right. So, for delta tending to 0, this will be like, say this little o delta is a very small term. So, this is like 1 minus lambda delta to the T by delta, right, which will be like e power minus lambda delta times T by delta, right. That is equal to e power minus lambda t. This is not a, this is the essential reasoning, but if you want to make this rigorous you have to say less than or equal to, greater than or equal to, etc. You can make it rigorous, okay, but essentially you will get e power minus lambda t, okay. So, x1 is exponentially distributed, then you have to prove that once that you got this x1 first arrival, then the time to next arrival, let us say x2 out here, so this is not x2, right, this is, then again for x2 you can make a similar argument, x2 you can make a similar argument because you have independence, right, that x2 is independent of x1 is clear because all the microslots are independent, right, and x2 was also exponential by the same sort of a logic, right, you can use the same argument, right. You will get x2 is also an exponential and independent of x1, all right. So, you get you can prove that these xi's are IID exponentials, okay, you can make this more formal, okay. That is the crux of the reason, okay. So, this also we can do. So, this question also you can resolve, okay. So, the equivalence between these three is shown. Now, one remark that I should make is that look at, I mean, to prove that something like the third definition which gives t, you know, these delta increments and specifying distribution in delta increments with SIP and IIP, that it defines a unique counting process itself requires a proof, okay. There may be multiple, potentially there may be multiple processes which have this property, right, that it is not the case and it uniquely defines a process itself, you know, proving it rigorously is a non trivial matter, okay. But we will not get into all that, okay. So, third definition is useful because I mean you can actually take these Bernoulli sort of processes with small time slots, you consider Bernoulli process and you can show that the joint distribution converges to that of Poisson process, okay. There is a result in the book which actually shows this convergence distribution of these joint distribution of these n of tj's, okay. You have a Bernoulli process, shrink the times in a certain way, you can show convergence to a Poisson process, at least the convergence of joint distributions you can show, okay. We do not yet know what a convergence of stochastic processes, right? That is there are many ways of many notions of convergence, we will not even get there, okay. But joint distribution convergence you can show, it is done in your book that the small micro slot Bernoulli actually converges to a this Poisson process limit you can show, not the process limit, but the joint distribution convergence in distribution you can show. Okay, so now the other remark I wanted to make is that if you want to, so there we have shown that these three definitions are equivalent, right. So, you could have started with any one of these, right. It is usually most people start with the first definition because it is the easiest to understand, but depending on what problem you are trying to solve or what application you are looking at, second definition or third definition may be more useful or more natural to use to solve that problem. Okay. So, for which application or which problem or which exercise which definition you apply depends on this particular problem you are trying to solve. Okay. They are all equivalent, of course, you can start with any of them, but it usually the case that one of them is the most convenient, and which is the most convenient definition to use, you get by practice, you have to solve lots of problems. Okay. Okay, so that finishes this module on equivalent definitions. Okay.